Very much. Thank you very much, Alejandra, for the introduction. Yes, so I'm Ignacio. I'm a postdoc at the University of Amsterdam. And yeah, the topic of my lectures is going to be the quantum properties of relativistic stars. So before we start, some disclaimers. So if possible, I would appreciate if you can have your cameras on. It's just more engaging for me and I think for everyone, but I understand if it's not convenient. Regarding the questions, Mariana and Ale just said this, so please ask at any time. You can either raise hand, you can write in the chat, I guess that's also allowed, or say if you want to ask questions even later, you can just drop me an email and I'll try to get back to this the next day. We're also going to have some time at the end of the day, maybe. Okay, so the plan for this talk is I'm going to review some conventional topics that you might be very familiar with in an unconventional way. So I'm going to focus on some aspects of these topics that you might have never thought about in detail before. And the idea is to try to explore some aspects that might lead us into some interesting research questions. I'm not here to tell you what is interesting or not, but I'm going to leave some ideas open and you can decide for yourself whether you think they're interesting or not. So the topic of the moment has been for a while, this movie, and I guess many of you have already watched it. We're not going to talk about the private life of Oppenheimer. We're going to talk about what he was doing before he was involved in the Manhattan Project. And you'll see how influential his last two papers were on this whole subject. So let's start with the with what we could consider the rapid or fast gravitational collapse. And this goes back to one of the two very important papers that Oppenheimer wrote with Snyder in 1939. And this paper has set the paradigm for this entire field for many, many years. So I know that you're probably familiar with this, but just to be on the same page. So this is the Penrose diagram of a collapsing star. So here, of course, we have sort of the radial coordinate going in this direction, the time component going in this direction. And the idea was that they studied an analytically solvable example where you could simply put pressureless dust. So you simply put pressure equals 0 inside the object. So this line over here, is the surface of the star. And you have a gas of dust that has no pressure. Of course, it has some density that is positive, and this thing starts collapsing under its own gravitational field. And we know what the endpoint is. The story is that at a finite proper time, if you measure proper time along this direction, at a finite proper time, you find a singularity. And they could work out this example in all detail. You can do it analytically. So now notice that this singularity is space-like, right? And it's in your future, right? It's something you encounter in the future. And moreover, it's hidden behind a horizon. Right? Those are the sort of qualitative features of the solution. They worked out an explicit example, but of course, later on, Penrose proved a theorem which tells you that more or less that under certain assumptions, which is the formation of trap surfaces and some energy conditions, that this qualitative picture would occur generically. So one important thing about this story, I think, is that, and this is very well known, is that in this case, if you look at what the curvatures are around the horizon, you'll see that they're generically very small for, say, stellar mass objects, for astrophysical objects. And that in turn means, as we'll see later on,
you have a question. So, Eloy.
Sorry, it's just a comment.
Yes.
Because the other assumption of the singularity theorem is the existence of
yes.
no compact Cauchy horizon.
Yes,
It's very important because there are examples where there are trap surface, there are null energy condition, but there are no compact horizons.
Yeah.
And they don't have singularities.
Yeah.
This is the case of regular poles.
Yeah.
Okay.
Thank you.
Sorry.
Yes, thank you. Thank you. I didn't want to go into those details, but it's a very interesting subject. Thank you. So generically, and again, there's also exceptions to this argument, but generically, because the curvatures around the horizon are very small, generically the quantum effects are very small. So the whole story is that while this process takes place, you can neglect the quantum effects completely. So this is, in a certain way, the fastest collapse, or one of the fastest ways that an object can collapse. So what I want to imagine now, or to consider, is what is the other extreme of gravitational collapse? What is the slowest possible process that can happen? This is discussed in a beautiful paper by Bondi, which is this idea of adiabatic contraction. So the idea is that if gravitational collapse now occurred extremely slowly in an adiabatic way, so that at each time the system is in equilibrium, then you can easily show that the evolution of the Einstein equations tells you that this system just follows a sequence of static solutions. So then the question is, in this other regime, well, what is the endpoint of this evolution? Okay, so we would have basically a sphere that starts collapsing and it starts becoming more and more compact. What is the endpoint of this? So at each point, we have a static solution. So this is static solution number 1. This is static solution number 2. There's some parameter that gives the flow. And the question is, where does this end? And the answer, as we will see, is related to something called Buchdahl's theorem. And basically, we're going to see this more in detail later on. Basically, if you look now, if you would draw the Penrose diagram of this process, at infinity, it would look very similar. And then you would have the surface of the star collapsing slowly along some orbit. And at some finite time, this thing, let's say here, this thing would develop a singularity. But that singularity would be at the origin. And it would have, so this singularity here would be time-like, and it would be naked. In the sense that it would not be hidden behind horizon. So the endpoint of this kind of evolution also leads to a singularity, but it's very different. And this is the sort of situation that I'm interested in understanding better, because the other one is very well understood. So the topics for today is going to be a review of compact objects in GR. We're going to look quickly at the TOV equations. We're going to look in detail at the solution for the interior Schwarzschild metric, then look at propagation of light in those geometries, and then discuss, give an example of the Buchdahl limit, and then explain Buchdahl's theorem and do the derivation carefully. Okay, so let's begin with the idea of relativistic stars. What does this mean? Well, this leads us to the other paper that Oppenheimer wrote with Volkov in 1939, and an accompanying paper by Tolman. So the problem, the setting, I know this is very well known, so I'll be brief here. You consider a sphere of an isotropic perfect fluid, which means that these pressures are all the same. And we put this on the background of a static spherically symmetric metric, okay? That thing contains two, in a gauge, in this gauge, it contains two unknown functions of the radius, which are f and h. So now, for that system, you could go and write down the Einstein equations. Now here, I'm just writing what the Einstein tensor is. We're going to look at these equations more carefully in a second. But basically, you have the component along t, along r, and then the theta and phi components are identical. And you see that here, the Einstein tensor depends on the functions f, r, and its derivatives. On top of that, we have the continuity equation, right? And because of the symmetries, this boils down to a single equation, which takes this form over here. Again, very well known TOV equations. Finally, we need to give some equation of state to close the system of differential equations. So if you think about how many equations and unknowns we have, so right here there are right now 5 equations, because there are 3 Einstein equations, then we have 1 continuity equation, and then an extra equation state. But of course, due to the Bianchi identities, one of them is redundant. So basically we have, so the number of equations is 4, and the number of unknowns is also 4, because we need to solve for the 2 functions in the metric, f and h, and also for the density and the pressure. So one very important example that is known for a very long time, it was found by Schwarzschild a few months later than he found the vacuum solution, is what's called the Schwarzschild interior star. So this is a very simple solution where you just, the equation of state that you choose is simply that the density is a constant. The pressure is something you need to solve for, but the density is fixed. So I'm just going to tell you what the solution is, and then we're going to look at its properties. So in terms of a single function, there's a single important function that appears here that I'm calling b of r, and it takes this form, where m, so here the idea is we have a sphere. The sphere has mass, ADM mass m, and then it has the surface or the boundary is at a coordinate rb. So
Ignacio, sorry,
yes.
you have a question in the chat.
Wait, let's see.
It says, I can read it for you if that's easier. Do you want me to read it?
Yeah, no, I see the question. I see the question. Okay. The answer is I am not sure. I don't know how to derive this from. I don't have it on the top of my head to derive this from a Lagrangian principle. I don't know. Apparently, no, says Eloy. Okay, good. This is just a perfect fluid. But maybe we could discuss later why not. Okay, so in terms of this unique function over here, here are the 2 functions in the metric. So the GRR is very simple. It's just the inverse of b, and then the lapse function takes this particular form, which involves evaluating this function at the boundary. On the other hand, you also solve for the pressure, and it takes this very simple form. Notice, by the way, that the thing that appears in the lapse function is the same thing that appears in the denominator of the pressure. In the exterior, you are gluing this thing just to the vacuum Schwarzschild solution. Okay, and that's the overall solution. So for this very particular solution, what does the Buchfeld limit, this singularity limit, mean? So that is the answer to the question, what is the last, in a certain sense, smooth static solution to the Einstein equations in this context? So I wrote here again the function b and the pressure and the lapse function. So what do I mean by the last smooth solution? Well, it's the last solution that is well defined, and you can see this in different ways. For example, if we look at the pressure here, clearly when this thing becomes 0, the pressure at the center, so I can evaluate the pressure at the center where it should be highest. So when the numerator becomes 0, this thing will tend to infinity, right? So the pressure at the center goes to infinity whenever we solve this equation equal to 0. So that gives us b at 0, is 9 times b at the boundary. And we have the function b. The function b is written over here. So what do we get? This equation implies, 1, which is the left-hand side, is equal to 9 times 1 minus 2m over rb, right? And we can simply solve this. Let me throw the 9 dividing to the other side. I subtract the 1, so minus 1 is 8 over 9. This is, it would be the other way around. So basically, I hope you understand what I'm doing. This is equal to this. That is the condition. And this leads to the condition RB over M is equal to 9/4. Okay. So this is the point, this is the value of the two parameters of the star, such that the pressure goes to infinity at the center. Now notice that the other thing that happens in this limit, there's two things that are happening. The pressure at the center is going to infinity, and at the same time, the lapse function of the origin is going to 0. Okay, these are the two sort of qualitative features that define, in this case, the Buchtel limit. So this is the first example of a formation of a Buchtel singularity. Notice that it is naked because if you look at this condition, so the compactness of this object, this number is much larger, it's a finite distance away from 2. So this has nothing to do with the Schwarzschild radius. This has nothing to do with trapped surfaces and so on. We're not talking about black holes. This singularity forms much before all of that could happen. Of course, I'm ignoring completely the topic of the stability of this object. This is just an observation of how the metric behaves. Last but not the least, notice what's happening to the Ricci scalar. So here I'm just writing down for you what the Ricci scalar is. And you can notice immediately that we said before, so the Ricci scalar here involves the two functions in the metric f and h. But if you remember, h was 1 over the function b. And if we go back and if we look at what b is at the origin, b is simply regular at the origin, b at 0 is simply 1. So h at the center is completely regular, but f here at the center is going to 0. Therefore, the Ricci scalar at the center is going to minus infinity. Okay, so that's another way of saying that there's a singularity, of seeing that there's a singularity forming at the center. Notice, by the way, and this is going to be very important tomorrow and onwards, is that for this particular solution, the Ricci scalar is becoming minus infinity at the origin, not plus infinity. That's going to be quite important later on. Okay, so one can understand this geometry better by looking at the propagation of light rays. So for that, we need to look at the geodesic equation. So how we do that? Well, you can just look at the action would be the proper time in general. And you would write this simply as, you know, the integral of dx mu over d lambda, dx mu over d lambda, sorry, a bit small, dx mu over d lambda times d lambda, where lambda is just some parameter. So this thing over here is basically the Lagrangian, and we can write down that Lagrangian explicitly for this particular example. Without loss of generality, we can just set the the theta angle to 0 because this thing is spherically symmetric. So if you just write down this Lagrangian, this is what you get. Again, very well known. Now this Lagrangian, as you can easily see, is independent of two coordinates. So it's independent. So dl over d phi is equal to 0, and dl over dt is equal to 0. That means that there are two conserved quantities that are the energy and the angular momentum. Now, in particular, if we look at null geodesics, tau is 0, so the Lagrangian is 0. And we can just replace these conserved quantities in the Lagrangian, put it to 0, and we get an equation of motion that takes this form. So here, this looks almost like a standard Newtonian sort of equation, with the only exception that the kinetic term is not standard because it comes multiplied by the functions f and h that appear in the metric, but that's fine, that's not going to be relevant for us. Then there's the conserved energy here, and most importantly, the potential. For this particular case, the potential goes as the lapse function divided by r squared. So now let's look at what the potential looks like. So this is going to lead to the idea of the photon sphere. So basically, again, we have this equation over here and the potential. So for this, what I'm doing here is I'm plotting So on the axis, we have the potential, and here we have R. So what I did here is to plot this potential for the particular solution that we just saw, this constant density star. So and the qualitative features of this thing are quite interesting. So, and I absolutely recommend to do this. It's a very simple exercise. So what you learn is the following. This metric has two parameters, the mass and the radius of the sphere. So if the radius is larger than 3 times the mass, what you'll see is that the potential looks like this, and it has no local extrema, has no maximum or minimum. So that means that the kinetic term could never vanish, right? In other words, there are no orbits where R dot can vanish. Now, right at the point when R becomes 3m, this thing develops a saddle point, and there's one extremum there. And if R is smaller than 3m, that saddle point really develops into two local extrema. The most well-known and discussed in many, many places is the one located in the exterior of the star. Because notice that right at this point, the radius of the star, the surface is below 3m, but this solution over here, so this point over here, first of all, it's a maximum. It's a maximum of the potential, and it's located outside the sphere, okay, in the vacuum part of the solution. So what this means is that if we have, maybe I'll draw it here, if we have the sphere over here, that corresponds to another sphere outside the star. And the fact that it's a maximum implies that this potential is unstable around that point, meaning that if you have a light ray, say, that is sort of hovering close to this thing, but not exactly, then it will either go away or fall inside, right? On the other hand, and more interesting for us, is that this solution has another photon sphere, but that is now located in the interior of the object. We put it in green. So this is going to be another sphere at the center where light can travel in circles. But the difference is that this one is stable. So if you have orbits that are sort of traveling close to this, but not exactly, they're going to be trapped by this potential. So now we can ask, well, what happens if we now look at the Buchdahl limit? So we just said that in the Buchdahl limit, we saw that one of the properties is that the lapse function at the origin was going to 0, right? But now we go back and look at the potential and see that, well, the potential is proportional to the lapse function. So if the lapse function at the origin, if f at 0 is becoming smaller and smaller, what happens is that this potential, we draw it now here, has a similar form outside, but then it becomes, sorry for my drawing, but it becomes flatter and flatter in the interior, right? Because the function f, which is this thing here, that is determining the shape of this potential, is becoming smaller and smaller at the origin, such that in the limit, really in the Buchdahl limit, this curve goes to 0 at the origin. So you lose the centrifugal barrier completely. Of course, because there's a singularity up here, that's not a surprise. But the interesting thing here is that in this case, the potential is going to 0 at the origin. And if you remember now the case of black holes, this is exactly what happens at the horizon of a black hole. Because the potential for that case, again, takes exactly this form. But for the case of the black hole, f is equal to 1 minus 2m over r. So if you evaluate this at 2m, this also vanishes. So the potential also vanishes there, right? That's the fact that the redshift is becoming infinite there. Pedro has a question.
Yes, sorry. In this case, you have I understand that f is going to 0, but you have a 1 over r squared that goes.
Exactly. Yes.
So which one wins? How fast is f going to 0? I don't remember.
Right. So for good question. So for any, even if you are an epsilon away from the Buchdahl limit, so that f does not vanish exactly at the origin, then the curve looks like this. It goes up again, because as you said, the 1 over r always wins. And the light ring in this particular example is moving towards the center. Exactly at the Buchdahl limit, which is of course singular, the centrifugal barrier simply disappears because f is identically equal to 0 at the origin. And then, yeah, that's the Buchdahl limit. Thank you. Okay. So this now leads us to to understand more what's going on in the background, and that's related to Buchdahl's theorem. So I'm going to first state the theorem, and then we're going to go slowly through the derivation, because it's very, I think, instructive. So, okay. So what did Buchdahl do? This is a beautiful paper. It's a very old, and I think this is one of the most important theorems in GR, but it's not as well known as, say, the singularity theorems. So what is the statement of the theorem? It's that if you take a static spherically symmetric isotropic perfect fluid, okay, same conditions as before, and you put it on this metric as before, then if you assume nothing about the equation of state, absolutely nothing, but only three things, namely that the energy density is positive, most importantly, that it is non-increasing outwards. Okay, so this means that if you were to plot the density, right, the density as a function of r, it has to look something like this, okay? Because you would, this is natural to expect that the star is most compact at the center, and the compact, sort of the density doesn't grow outwards, and you assume the Einstein equations, then you can prove that there exists no static solutions that are smooth beyond this point. Again, when the radius of the sphere divided by its mass, has to satisfy this constraint. Of course, this depends on dimensions and boundary conditions and so on. This is in 4 dimensions for asymptotically flat solutions. So this is usually sort of interpreted as a kind of an absolute upper bound on the compactness of a sphere. And again, this is the way how it's written here. It's not really telling you so much, but as we already learned before, this is related in a deeper way to the formation of this time-like singularity. So what I want to do now is go slowly through the derivation to see exactly where do the assumptions, where are they important, and what's the idea behind. So by the way, I'm following not the original derivation by Buchdahl, but the one that is in Walt's book, which is very clearly explained. So how do you prove this theorem? So we go back again to the Einstein equations for the static spherically symmetric perfect fluid. So we start with the first equation, so the TT equation that I wrote here again. The first step is that this equation can be integrated immediately, and that's very easy to see. So on the right-hand side, we see that everything depends only on one of the functions, which is h and its derivative. So you can take this thing and simply multiply by r squared. Okay, so here we get this rho times r squared. And on the left-hand side, there was 1 r to the minus 1 here. So we get r h prime over h squared. Then this r to the minus 2 disappears, and we get 1 minus h to the minus 1, right? And now you can immediately notice that this is precisely what is written down here. So this thing is the derivative of this. So say, for example, we take the derivative of this guy, then this is what survives, and that's the second term here. On the other hand, if we take the derivative of this, we get an r. That r is the one over here. And then the derivative of this simply gives us h prime over h squared, right? Because there's this minus over here and here. So if we now take that equation, we can integrate it from 0 to some arbitrary radius, right? So we take this equation now. Let me do this in another color. And we just integrate this. So what do we get? On the left-hand side, we get the integral. So let's integrate from 0 to r, r squared rho. And on the right-hand side, we just get a boundary term, r times 1 minus h minus 1 from 0 to r. So the left-hand side, we just leave it like that. Now, if you look at the right-hand side, and now you see where the first assumption appears, is that this thing contains two terms, right? The first term is just this, 1 minus h minus 1. But we would also need to evaluate this at the origin, right? Now, at the origin, r is going to 0. So provided that, so if h at 0 is regular, it's not going to infinity, that boundary term cancels because there's a factor of r in front. Okay, so here we were assuming that we didn't state this directly before in the theorem, but we're assuming that the metric is regular. Okay, and when you solve this equation over here, okay, so this is the solution basically, and you just rewrite h in terms of another function that we call m, and just throw this thing to the other side. You get this. I know this is very well known, that h takes this form, where the mass is the integral that appeared by integrating this term. And this mass has an interpretation and so on, but we're not going to talk much about that. So this means we solved the first of the Einstein equations, and here already you can see a first sort of result on a bound of the compactness, namely that we require for the metric to be non-degenerate, right? We need to require that h at 0 is positive, or non-negative, right? Because otherwise the signature in the metric would be changing, right? The determinant of the metric would change sign, and that would be very bad. So we want to avoid that. So the requirement that h at 0 is positive or is not negative leads to this equation over here, right? And that already gives a sort of a local bound on the compactness of an object. And is, of course, if you look at this is basically the same condition. This is the condition you would get for a black hole, right? But that's not the most, that's not the strongest constraint that the Einstein equations hide. So, okay, we got rid of the first equation. So the next step is that we want to derive an equation that does not involve the pressure, because we wanted to make a statement that was independent of the equation of state, right? So how do we do that? One way of doing that is that if you look at the Einstein equations for this case, the RR component and the angular component on the left-hand side in the stress energy tensor, because it's isotropic, they are identical. Therefore, if we subtract these two equations, we completely get rid of the pressure. And that's the trick. So here are the other two equations we had. And now we're going to proceed to manipulate them a little bit. So now let's do the following. So if we take the angular equation, what happens if we now subtract the other equation? So on the left-hand side, we get 0. And on the right-hand side, we have a combination of terms. So let's say, okay. So first we have this red term over here. Okay, I'm going to just rewrite it again. fh minus 1/2, and then the derivative of this thing over here. Then you will see that the next term here is the same term as the first one in the first equation, right? The only difference is the coefficient, which is 1/2 in the second line, and it's 1 in the first line. So because we're subtracting, so we're doing the second line minus the first line, this becomes minus 1/2 of RFH minus 1 times F prime. right? Now we're left with this term, the last two terms over here, which I'm going to write in red, and you're going to understand in a second why I'm coloring and sort of associating them in this way. So we have the first term, it's -1/2 r h squared to the -1 h prime, and then because we're subtracting the first equation, we get a plus r to the -2 1 minus h to the -1. So that was the first step. We have one equation where we eliminated the pressure. So the next step is that we replace the solution for h. So we just said that h takes the form 1 minus 2m of r over r. Okay? So we can replace that in these green terms, because this in turn means that if I take the, h minus 1 takes this form. We can take the derivative, so let's take this, let's take this equation and take its derivative with respect to r. Okay, so on the left-hand side, we get minus h prime over h squared, right? And on the right-hand side, we get -2 times the derivative of m over r, which is, we can write it immediately down, actually. We get -2, and this, let's say we take the derivative of m first, this is m prime over r, and the second term is minus m over r squared, right? So that means that if we just collect now the green terms, right? We go here, oops, and here. So the green terms, we get the following. So the first term is -1/2, and I'm gonna probably need help here. If I make a mistake, please correct me immediately. I get this thing wrong all the time. So the first term goes like r to the -1, and then h prime over h squared. And then in the second term, yeah, we have, well, the same thing, r -2, 1 minus h inverse. So now we can just replace, because from here, right, so we immediately see that 1 minus h to the -1 is equal to 2m over r, and we can replace that in the second term. Right, so here we get r to the -2 times 2m over r. So since we have this r to the -2, let me get rid of this one and just write this as r to the power 3. And on the other hand, for the first term in the last line, we already computed minus h prime over h squared right here. Right, so we can take this thing and replace it over here. So what do we get in that case? Notice that there's a factor of 1/2 here, and there's a factor of 2 here. The minus is already included here. So this minus carries on, right? It doesn't cancel. So here we get a minus r to the -1. And I'm going to write these two other terms. So this is m prime over r, and then minus m over r squared. And now finally you see that here, this term, the last term over here, is of the same form of this one, right? So all in all, what we get from only the green contributions is minus m prime over r squared. And then there's a plus 3 times m over r cubed. I hope that's correct. If it's not, please just correct me immediately, but I think this is correct. Because finally, we can write this thing as the following. So if you write this as r times minus m prime over r cubed plus 3m over r to the power 4, we can see that this thing is an exact derivative, and it's namely the derivative of should be the derivative of m over r cubed. Is that correct? Sorry, it's minus the derivative of this. There's a minus over here. Right, because that's easy to check. If we take the derivative of this one, we get m prime, which is the one over here with a minus sign, divided by r cubed. And if we take the derivative of the second term, we get a minus 3 over r to the fourth. With this plus sign, with this minus sign, we get this plus sign. So this is a total derivative. And I'm doing all of this carefully because this is sort of the essence of the derivation, to manipulate things, to turn them into boundary terms, and then have some assumptions about what's going on so that you can say something non-trivial. So let's now go back to the equation and replace this thing. So what we had was, we're going to copy this equation over here. This was the red contribution, which we haven't touched so far. So we are going to put it here. And then we had plus, so the contribution of all the green terms, which now, simply reduced to this. Okay, and this is the resulting equation. Let's erase this guy. Okay. So now, let me replace again what we had here, what this square bracket was standing for. So that's this term over here. So it's fh to the minus 1/2 times f prime. So this was f h to the minus 1/2 times f prime. Okay. So what can we do now? So the next step is, we have one more step to go. So let me divide this whole thing, so multiply by 1 over r. Okay, and we can do it directly here. So in the last term, I get rid of this r, and then I have a r to the minus 1 here, and another r to the minus 1 here. And if we did everything correctly, then we should see another total derivative showing up here. So how do we see that? Let's see. Yeah, okay. So the last step is that we multiply all of this by fh to the power 1/2. And then we're done with this part. So why am I multiplying by that? Because that's the term that appears over here. I want to get rid of this term. Okay, so let's write down once again the final equation we have. So this is 1/2 of r to the minus 1, the derivative of fh to the minus 1/2 f prime. And then we have, notice what we got here. So we have also 1/2, and we have an r to the minus 2, right? Because we have an r to the minus 1 here and another one from here. And then we also have fh, but it's to the power minus 1. So together with this 1/2, we get a minus 1/2. We get fh to the power minus 1/2 times f prime minus this boundary term. So now, so the last step is that now this should turn also into a total derivative. Hopefully, if this went correct. So let's see. So this looks like the derivative of r to the minus 1, fh to the minus 1/2, f prime, and that's it. Let's check if this is correct. So if I first forget this first term, and I take the derivative of all of this, that is contained in this first term, right? On the other hand, if I don't touch this, but I take the derivative of the first term, this r to the minus 1, I get a minus r to the minus 2.
Ignacio?
Yeah.
There is a minus, right? I mean, maybe.
Oh, sorry, where? In between them?
Yes.
Yeah, exactly.
Because
So
otherwise
this
they
minus,
don't cancel.
yeah, this minus comes from taking the derivative of this one.
But they should cancel, right?
No.
I don't know.
Yeah, no, we're not trying to cancel them. We're trying to write this as the total derivative. Yeah. Good.
Perfect. Okay.
So this minus, so this minus over here is related to the derivative of this term over here. That's why you get this minus r to the minus 2. Okay, so I promise that we're done with the hardest part of the computation. It wasn't that hard, but we need to know the tricks. And I think that just reveals the genius of Hans Bochtel to realize how to do this thing. So we have that finally this is the equation. Well, actually, I'm not gonna, times this, because I already wrote down this equation in the next slide. Last but not the least, the only difference between this equation and this equation is that you see here the, I just wrote down the derivative, this derivative of f. There's an f to the minus 1/2 here, so you can just collect that as the derivative of f to the power 1/2. But otherwise, the equation is exactly the same. So then now comes one of the most important observations of this theorem is that, so we have an equality between these two things. Now, remember that what we assumed was in the theorem was that rho prime was non-positive, right? The density was non-increasing outwards. So this means that the function m of r, it cannot increase faster than r to the power 3. And the reason is because the constant density solution just saturates this bound, right? So imagine for a constant, if rho is, right, so if rho is constant, if rho is some constant rho, then remember that m is proportional to the integral of r squared times rho. So if rho was a constant, you simply get that this expression grows as r cubed. Therefore, if you divide it by r cubed, this thing is just 1. It's a constant, right? It's just constant. Therefore, its derivative, if you would replace it here, the derivative would be 0, right? That would be sort of a limiting case. Now, we already said that the density, but you could ask, well, what if we take another function? So, okay, suppose you take rho 0, this thing, then you need to put minus some positive number, say times that. For example, take just some stupid trial function where alpha is positive, and it has to be positive because, again, we said that we wanted the derivative of this function to be non-negative. The derivative of a constant is 0, so the last thing is the only thing left. So if you were to replace this in this expression, you would get a constant and then minus something that in this particular case goes as r to the 4th. So this would mean that if you take now the derivative of this thing, this would be negative, right? So this means that the constant solution saturates this bound. So for any other trial function that satisfies this constraint, the right-hand side of this thing is going to be negative. And that leaves us with the situation that we wanted, because now we have that the total derivative of something satisfies this bound. So we can just take this equation and you simply integrate it from some radius r to the boundary, and you get two terms, right? We get r boundary minus 1, h minus 1, everything at the boundary, times the derivative of r f 1/2 at the boundary minus the same thing evaluated at r is non-positive, But now you see that at the boundary, this thing becomes the Schwarzschild solution. And for the Schwarzschild solution, H, so here we're almost done actually. So this here you can use, here you can use the exterior metric, right? Because we're at the boundary. And in that case, H to the -1 is simply 1 minus 2m over r. That's the Schwarzschild solution. F is exactly this. So you know how to evaluate this term, right? So namely, this is rb to the -1. We evaluate h to the -1/2. So this is simply 1 over 1 minus 2m over rb to the power 1/2. And you can, again, evaluate the derivative of this function. It's very easy. I see that I'm sort of running out of time. But you can imagine, you just take this f, take the derivative, replace it here, and you get something very simple. So you're going to get an inequality between two objects. One of it is evaluated at the boundary and depends only on the properties of the two parameters of the star. And on the other hand, you will get something that depends, that is a function of the radius, right? And this is what you get. I don't want to go over time, so just going to take 1 or 2 more minutes if Alejandra allows me. 1 minute. Okay, good. So we just here we just used a continuity of these functions at the surface because I used the exterior solution. So then you get this really nice inequality, which now you can use, which is the one written down here. So basically, but here you see the last part is very simple because you can just take this inequality, throw all of this to the left-hand side, and then integrate through the entire sphere, okay? And then you have everything you want. On the left-hand side, you get something that depends only on the integral of the function h, and on the other hand, you get some boundary term that depends on f. So you see, this is going to relate the function f at the origin with the function f at the boundary, and the function h throughout the star. And this is what this last inequality, this is what you get. I'm sorry that I'm rushing over this part, but I think the most important part we already covered. So here, finally, you get something that involves the central value of the lapse function, the parameters of the star, and then the only thing that is left to do is to, that has not been integrated, has to do with this mass function. And again, by exactly the same arguments as before, you realize that it's the same equation written again, is that for the fixed total ADM mass of the star, again, the constant density solution provides the bound for this problem for the same reason as before. Namely, this depends on the trial function for the mass that you choose. If you choose the mass function associated to the constant density solution, then that solution maximizes this whole thing, which means that all of this is going to be smaller or equal than its value for the constant density star. And when you evaluate that for that very simple example, this is the inequality you get. So you got rid of everything else. The only things remaining are the lapse function of the origin and the parameters of the star. And the last condition that you use is simply that you want that the star has to be regular. So the lapse function of the origin should be positive. Again, the same reason as before. This thing should not change its signature. And this condition, if you just solve this equation for this condition, leads to the condition that RB over M has to be larger or equal than 9 over 4. And that is, well, the statement or the result of Buch's theorem. Okay, so let me just, I'm going to skip that slide and just leave you with the take-home message. So if gravitational collapse occurs sufficiently fast, then it's going to look essentially like the Oppenheimer-Snyder problem. The quantum effects are going to be very small because the curvatures at the formation of the trap surface is very small, nothing happens. But if gravitational collapse occurs slow enough in this adiabatic sense, then the final state of this evolution is not the formation of a horizon, but rather you hit the Buchwald limit. What we saw is that in that case, what happens, the most important things that happen is that the central redshift goes to infinity, just like in the horizon of a black hole. This was this statement over here. And on the other hand, there was a naked singularity that was time-like and is developing in the interior. So the plan for the next two lectures is tomorrow to understand a bit better how these singularities look like. And then we're going to see that introducing relativistic quantum mechanics is essential to understand them. And in the last lecture, the question will be what happens if we include quantum field theory in this picture. So with that, I'm done. Thank you very much.